Welcome everyone to the second part of 8 in the series of the Starburst Foundation Subquantum Kinetics number 2. So last time we sort of left off with the at the point where T.T. Brown had bootstrapped or put AC on top of DC. And at this point, the Navy and whoever he was working for basically made everything dark and black. And that was the end of the 50s, I think like 58, 59. And by 1960, all of the information on electrogravitics was literally nowhere to be found or very, very hard to find. And for, all these years, they've kept it that way. So we're going to talk a little bit more about this stuff. I guess we can't share the pages today, but this is going to be page 6. And just so everyone knows, the pages on the way I mark them is I only mark the front page. So it'll be 6 and then the back page. So we're going to get to page 10 today, which will get us actually to 20. So we did 10 last time. We're going to do 10 this time. So a variation of the electric field concept, Bronson's idea was to place a parabolic metal grid between a positively charged parabolic lift canopy and a negatively charged sphere. So on page 6 at the bottom, there's actually a picture of that I drew of what we're talking about. But essentially, it's like a half round canopy with a
Eddie, Eddie, to interrupt you a moment, would you like me to try and share that if I can?
Yeah, I mean, it'd be better if we could, right?
So Amber, if you let me share, I think I can automatically share. I can share. Okay, so let's just do that, and I'll go to.
Yeah, you should be able to share.
Yeah, I can share now. So whoops, Daisy. Let me just work this out a minute.
Okay, cool.
So,
yeah, because it'll help. It'll help to. I'll let you do that, Brendan, and I'm going to keep going with this.
Yeah.
So then he applied an oscillating high voltage field between the lift canopy and the negative sphere. He chose a megahertz frequency for this oscillating field that would establish a resonant stationary wave between the two electrodes. Okay, so last time Amber asked me if it was a wave that got set up between here, and it is absolutely a wave. And it has to be sort of tuned. The wave has to be tuned for the distance. So everything has to sort of jive that way. And they do use megahertz or even higher into the gigahertz frequencies. So that was from last week, Brendan.
Yeah. So what are we doing now?
We're doing the stuff I sent yesterday.
Okay, yeah. The ones you sent yesterday. Okay, so I'll find that one.
Yeah, and it starts with page 6. So essentially, what they're doing here is he is creating this stationary wave, also known as a standing wave. With everything that I do in audio, that's exactly what I call it, is a standing wave. But the other thing to understand is a standing wave is a soliton, and that's the way I understand the terminology. So he chose a megahertz frequency for this offsetting field that would establish a resonant stationary wave between the electrodes. He hypothesized that this electrode.
Eddie, is that page 6? Page 6?
Yeah, it's the front of page 6, you betcha. And then we're perfect. And then we're sort of at the bottom, or going towards the bottom there.
You can see it on the screen then.
Yeah, you betcha. And the drawing is at the bottom there that I was first talking about.
Yeah, so you can see it on the screen just to confirm.
Yeah.
Yeah. Okay.
It's
great.
Perfect. Yeah. Thank you. So he hypothesized that this electrostatic, so that's important, electrostatic stationary wave would somehow store the energy of the applied AC field in ether-like reservoir residing in the space immediately around the test device. So what he's saying is that the energy gets, the charge, because that's what it is, gets stored in this ether. And of course, we talk about the ether all the time. So he felt that this resonant condition might allow the latent energy in the stationary field to be used with a minimum power consumption. So what he's trying to say is, in this mode, the power consumption is very minimal. So it's essentially a very, very good setup. Now on the next page, which is the back of page 6.
Is that the correct one?
Yeah, you betcha. Unconventional shock discharge Coulomb waves, sometimes called longitudinal waves. So part of the problem with all of this is there's so many different names for things. We try to sort of focus in on the important stuff, and longitudinal waves are absolutely important thing. But that description of unconventional shock discharges, or Coulomb waves, they are sometimes called longitudinal waves. So the ether physics of subquantum kinetics conceives quantum structures such as the subatomic particle and energy waves to be concentration patterns that emerge in a primordial reaction diffusion ether, one whose constitutes both diffuse through space and react among one another, according to a specific set of non-equilibrium reaction processes. So again, the non-equilibrium is really important. So model G involves just 7 types of etherons for its specifications. So a lot of people don't know that there are different types of etherons. Brandon would know. So there is the A, the B, the G, the X, the Y, the Z, and the ohm, or it's the ohm side for omega. Subquantum kinetics identifies etheron concentrations at any given point in space with the standard energy potential concept. So now we're on to the next page, which is page 7. A Spartanal variation in the electric field characterized by a Spartanal variation in the electrical potential would correspond to a Spartanal variation in X and Y etheron concentration. So now he's going to start talking about how these etheron flows happen. A gravity field characterized by a Spartanal variation in the gravity potential would correspond to a Spartanal variation in the G etheron concentration. So G for gravity. Now this is really, really, really important, like the most important. And I've written in the margins a few times because I've sent this to so many different people and trying to focus in, but I said it's very, very important, the most important. And he's talking about subquantum kinetics supposes a cosmology of continuous matter creation rather than a single Big Bang creation event. So this is so, so important. There was no Big Bang. I said big words, but true. So this is a really important part of subquantum kinetics. And we know that it's an open system, so it doesn't rely on all the energy came from this one explosion that happened at the beginning of creation. In fact, with subquantum kinetics, every time the Turing wave goes in and out because it inverts on itself or it blinks, the entire universe is recreated. So this is so far differently than the Big Bang theory, and we need to get past the Big Bang to move on. So positive polarity fluctuations are a region of high Y and low X etheron concentrations, and the negative polarity fluctuations are a region of high X and low Y etheron concentrations. It's an open system characterized of the ether. Now we're on the back page of that one, Brandon.
Yeah, okay, next page.
Yeah, the back page of it. Yeah, you betcha. So waveform patterns configured of etheron concentrations whose magnitudes vary cyclically through space. The wavelength of the electric field pattern would equal the particle's Compton wavelength, which is numerically equal to the wavelength of the photon that would result if the particle's rest mass was not converted entirely to energy. So now we have the Compton wave formula, and it is essentially, it's, I don't know what
Lambda
that
equals Planck's constant.
is. That
Speed of light
okay?
over
That
energy. And
yeah,
E is rest mass, H is Planck's constant, and the
yeah,
Compton
exactly.
wavelength is equal to the Compton wavelength. C. Okay, C is equal to the velocity of light.
Yep. So those are the factors: the Planck's constant, the velocity of light, the rest mass, and that's did you say it was lambda? I think
Lambda is the wavelength. It's
when
is measured in as length and as displacement. Like distance is measured in terms of meters or micrometers.
And the Compton wavelength would measure just 1.32 times 10 to the minus 13 centimeters. So it's really, really small. Electrons wavelength would be about 2,000 times longer. So somebody asked me at one point, I think in the other group, at what level is all of this? Well, this is saying that the electron's wavelength is 2,000 times larger than the Compton wave, and we actually know that I think there's stuff below the Compton wave as well too. Subquantum kinetics calls this wave-like field the particle, the Turing wave, and this is exactly the simulations that Brendan has worked on, is trying to produce this Turing wave in a computer simulation, which they were successful with in 2 dimensions, I think. Brendan, is that correct?
Yeah, 2 dimensions. We did do 3 dimensions, but it was a bit unstable.
Yeah, and I think we need a bigger computer setup to really get to that point as well. Which is something that Amber is actually hopefully going to help us with in the future here. So that's fantastic. Subatomic particles that model G forms do not disperse over time. So now we're on to the next page. And we're talking about these cyclical transformations of X into Y and Y into X is what allows the Model G reaction system to create and maintain the subatomic particle's stationary wave pattern. Okay, this stationary wave pattern, again, is the most important thing that there is, because the Turing wave is actually, the etherons create the Turing wave, but it's just it's a stationary wave pattern, just like with cymatics. There are certain patterns that go a certain frequency, so it is a frequency, but it is seen as a sort of like a cymatic pattern. And I think actually, Brendan, that it has to be done in 3 dimensions, but in reality, it actually has to be done in 4 dimensions, because once you've got it stable in 3, now you need to apply that particle and see what happens over time. So it's almost like the ringing of a bell. Like you've got the initial tone and then you've got all the harmonics behind it. So I think in the long run, that's what's going to happen. And in New Aerospace Technologies, the book that I was asked to edit and have a look at, there are 2 chapters, and one is 4-dimensional resonance, and there's another 4-dimensional one in there as well too, and that's something that we should look at. Maybe in this group we will in the future once we get through some of this stuff.
Yep.
So
we're okay to have a break after on the top of the hour. Is that okay with everyone?
Yeah, I don't think we have that many.
5 or 10 minute break and then come back. Are you okay with that?
Oh, sure. Once we get through the papers,
not half an hour. Anyway, we'll see how it goes. We'll see how it goes.
Yeah, let's try and get through the papers here first, because we're going pretty good. We're about halfway through them right now. So, where was I? The Model G reaction system. Okay, cyclic transformations of X into Y and y into x is what allows the Model G reaction system to create and maintain the subphonic particles' stationary wave patterns. Super important. Two gravitational mass polarities, each concealed within a corresponding electrical polarity. Positively charged particles such as protons have low X-on concentrations in their cores, and they should produce a central gravity potential well, so a hole or a well. Negatively charged particles such as electrons, which have high X-on concentrations in their cores, should produce a central gravity potential hill. So
Right.
this is the well and the hill that we were talking about in the first section, right? And if
Hey,
we go
Eddie,
to
can I make a comment?
yeah,
So one thing that's interesting about this is that you are it explains gravity as an energy potential, which is how we understand voltage. You know, voltage is a difference in
yeah,
charge effectively between two different things, and it's a potential difference that allows the transfer of energy. And this model for gravity is like a potential, just the same as voltage.
absolutely, super correct. Because it is really the voltage potential that is causing the gradient to happen, and that makes things flow. So we get the etheron flows and stuff, right? So absolutely correct. Yeah, definitely. We need to talk about voltage potentials more. One of the things Chris Beskar, the CEO of Stavati Aerospace, we've talked about stuff before, and he believes in this electric universe idea. And I said to him at one point, I said, it's an electric universe, but a better description of it would be an electrostatic universe, in my view, sort of thing.
This
So,
video on
yeah.
Starburst Foundation and etheric.com if you like. Eddie, anyway, we'll see how it goes.
Yeah. So now we're on to the next.
If everyone's okay with that, only if people are okay with that.
Sure, absolutely. On the next page, we've got some drawings of what basically we just talked about. So that'd be the back of page. The next one.
Next, what you want me to go on to the next page?
Yeah, and we'll show you the. So here at the top we have Y-on concentration or electrical potential, just as Mark just said. And the Y-on generation, it shows you that it rises and comes back down, and the electrical field is essentially what you're graphing, and the positive charge density lays in that area where there's at the top of the curve essentially, and then it comes down. So the bottom part shows G-on concentration or gravity potential. So this is obviously the opposite. It's still sort of like a curve, and the same thing applies. The curve is the gravity field, and the positive mass density lies in that section that's just sort of directly under the hill. Or actually, this is a well. So the top one is your hill, and the bottom one is your well, essentially. So that sort of shows it. And these are all drawings from Paul's books, right? This would be probably from The Secrets of Anti-Gravity, because I actually don't have Brendan sending me the first subquantum kinetics book, and I haven't read any of the other stuff. So this is all from Secrets of Anti-Gravity Propulsion. So now we're on to the next page, and we're going to talk about the wells and the hills again. A proton's gravity well would have a matter attracting effect on the surrounding neutral matter, while an electron's gravity hill would have a matter repelling effect on surrounding neutral matter. So he's sort of explaining again, the proton has the well, the neutron has the hill. Now, this part is ultra, ultra important, and I wrote ultra important beside it. A particle's Turing wave structure is recreated every instant. So this is the actual blinking universe that is a dodecahedron, that standing wave pattern that comes out, inverts on itself, and goes back in. And when it goes back in, when it comes out, it's in space-time, and when it goes back in, it's in time-space. So we have to understand that this thing fluctuates back and forth, and it recreates our entire universe every single time it blinks. And at some point, I'd like to be able to find, and I know it's in Paul's book somewhere, the frequency that he talked about that this Turing wave is actually blinking at, or coming in and out as. So a particle's Turing wave structure is recreated every instant. As etheron diffusion balances etheron creation or dissolution at each space and point, because the solid state condition tends to create a symmetrical space structure for the particle, any such departure from symmetry will induce a stress, and this is really important because it's the stress that actually matters here. Any departure from the symmetry will induce a stress or a state of non-equilibrium. This stress is identified with the electrostatic or the gravitational force that the electric or gravitational potential field exerts on the particle. So again, really important that it's a stress that's set up, and it's creating using electrostatic force, and this exerts the electric or gravity potential field on the particle. It is perfectly accepted for a field to accelerate the very same charges that generate it. This field anatomy is the key to understanding how unbalanced electrostatic forces can induce motion in an asymmetrical capacitor. So this is really important. Again, it's the unbalanced forces, and they're inducing motion in an asymmetric capacitor. T.T. Brown's experiments are all about asymmetrical capacitors. So we can go to the next page there again, Brendan. What's really important also to know is that this asymmetrical capacitor is also known as a gun diode. So GUNN diode. You can buy them. International Rectifier actually has them, but they're very small powered, like they might be a 1 watt one or something like that. They're not powerful enough to induce this pondered motive force, but larger ones were built for the Navy and for the military and whatnot, and they're used extensively. And in fact, the wing of the B-2 bomber is packed with this material. That's what makes it antigravitic. So these materials and what we do with them are really, really important. So by oscillating the electric field to repeatedly create virtual charge, so they oscillate the field, and the charge actually starts to build up and build up and build up and build up. So that part's kind of important. The gravitational thrust may be maintained without cancellation. So he says, by oscillating the electric field to repeatedly create virtual charge, the gravitational thrust may be maintained without cancellation. The electrogravitic force should increase as the electric potential field across the capacitor becomes increasingly nonlinear. So we're back to this nonlinearity again. The more nonlinear the field, the greater the induced gravitational thrust. So this is a real key to it. If you want more and more thrust, you need to make it more and more and more unlinear. Force also increases in accordance with the dielectric constant and its mass. Thus, dielectrics with higher K and greater mass will deliver greater thrust. So the higher K matters because that's kind of like the efficiency of it, but how much mass, how big it is very important too, because the more material that you have, the more thrust or energy that you can draw to the system, essentially. The thrust developed by the device could be maximized by incorporating high mass semiconducting materials in the dielectric near the negative pole, where the gravity potential is greatest. So they're talking about now engineering this Ki-K material in different places within that canopy and ball, essentially. The amplitude, and this part is ultra important again, the amplitude of the AC quarter wave resonance should be kept below 100% of the negative DC bias voltage. You have to go to the quarter wave theory sort of to understand what they're doing here, but it's very specifically saying that the amplitude of the quarter wave resonance should be kept below 100% of the negative DC bias voltage. In the future, I think I'm going to talk about vacuum triode amplifiers. Mark will know what I'm talking about, and we'll show how you apply a negative voltage to actually get the tube to work. And tubes are literally like a little environment all to their own, where there's charge and voltage and all kinds of things going on with inside them. So once you understand how they work, and by the way, Nikola Tesla, in 1940, he retired as the vice president of worldwide engineering for RCA, an RCA tube company, which were the highest, best technology on the planet at the time. He did not die poor, although everyone seems to think that he did. It's not the case, actually. The New Yorker Hotel, as a matter of fact, was another Wardenclyffe. And I actually saw the secret library, or the secret lab space that Tesla used to do all his experiments in, on a video years and years ago. Somebody showed me. The fanning geometry of the spark discharge would have created a non-linear electrical potential gradient between the capacitor plates that in turn would create a virtual charge density between the plates. So again, we're going back to that virtual charge, how it's important that we need to set all that stuff up to make all this work. Okay, I think we're on the last page now, Brendan. So page 10. So we'll just be the front and the back of this page. This then would have a momentarily, this then would have momentarily generated a gravity potential gradient. Now, when I did the theory of anti-gravity with Stavati Aerospace, it was all Paul's words, essentially the theory. But I did add one sentence, and I said I think that the key to anti-gravity is a gravity gradient. So that's really important. So this then would have momentarily created a gravity potential gradient across the capacitor's element. While the virtual charge were present, however, they would have generated a substantial gravitational thrust on the rotor. So again, we're talking about how this virtual charge, which comes from the time-space side, comes into our existence, and once the charge builds up to a certain point, you can get these thrusts occurring. Brown's observation that he obtained greater thrust when he used barium titanate dielectrics. So I've talked a little bit about the stuff at the beginning. Barium titanate has a higher K and is a much better material. There is another material called BZT, which is barium titanate with zirconium, which is even better. That has a K of 23,000. So it's probably exactly the stuff that they pack into the wings of the B2. And by the way, it's not just the B2 that are anti-gravitic. The F-22, the F-35, the B2, the B-21, the NORAD version of Air Force One, these are all anti-gravitic hybrids. They have both conventional systems for propulsion, and then they have advanced systems for propulsion. And there's literally a switch on the dash that says coast mode. So when you put it into coast mode, you're actually switching into electrogravitic mode. Now, there's a young Marine who me and my best friend Al are mentoring, and I told him that I saw a picture of an F-35 fighter sitting flat in the water right beside an aircraft carrier that somebody sent me. And I told him that if that switch was turned on, that plane would be sitting in the water and wouldn't even be getting wet. And the next thing that happens is that F-35 will just come straight up vertically and land on the deck of the aircraft carrier. So these are all hybrids, and they've been hybrids for a really long time. I personally know the NORAD pilot that flew Air Force One with Bill Clinton, and we talked about the NORAD version because my father was part of NORAD and he's part of NORAD, and how it is anti-gravitic. Essentially, it can stay up there indefinitely. So the electrogravitic force exerted on an intervening dielectric should vary in proportion to the dielectrics permittively. And this is a property. Yeah, sorry, thank you. And that's a property that is really important. A dielectric such as barium titanate has a high K, has a K value of about 10 to the fourth. So it's around 10,000 or thereabouts when slowly charged. But when rapidly charged over a few milliseconds, its K value will be much lower, perhaps 1,500. So what they're saying is these K values don't necessarily apply to the really rapidly charged things. The dielectric constant will go down, but it's still there though, and that's what allows the stuff to work. Dielectrics having greater mass would produce greater thrust. So we're back to the more material that you have, the better the motor, because this is essentially a motor that connects the ether and allows these craft to fly. The dielectrics having a greater mass would produce greater thrust. He envisions a low K and mu region as manifesting a high pressure. So when we're trying to fly a plane, it's all about differential pressures. So there's, you need a high pressure here, you need a low pressure here. He's explaining how this is done essentially right here. So so the low K is the high pressure, and a high K would actually manifest a low pressure region, and the gravitating body would migrate towards that of a high pressure region. It would migrate from the high pressure region towards a low pressure region. So again, you're creating what Mark talked about there, a voltage potential. This is just a gravitational potential, and they're definitely connected. So this is the last page, Brendan, the back of page 10, which says subquantum kinetics offers an understanding of how fields are generated and how they exert force. It predicts the autogenetic creation of subatomic particles having charge, mass, spin, and matter having properties. Brown adopts a mechanical model when he suggests that the etheric field creates a pressure upon a material body. Subquantum kinetics addresses the question by providing an understanding of how a material body and etheric reaction diffusion pattern wave migrates in response to the influence of an etheron concentration it's basically a potential gradient, and what I was trying to say there is it's an etheron concentration gradient. So we're back talking about gradients again. Subquantum kinetics also predicts in detail how a mass locally decreases the geon concentration to create a gravity potential well in its vicinity, and also how a charged particle generates a corresponding decrease or increase in gravity potential depending on its electrical polarity. So I just decided just to do like 10 pages at a time so we can we can sort of leave it out there. And is there any questions or anything that you guys want to bring up that we talked about before we stop the recording?
I think I had a question real quick, and I'm trying to remember what my question was.
Sure.
Oh yeah, you mentioned spin.
Yeah.
I don't know if I don't know if you would know the answer to this, or if Brendan would know the answer to this. But I remember back when I was taking modern physics for my undergrad, they said that spin is not like particle spin is not like actual spin. But I want to know from either of you guys if that's actually true or not, because I was like, well, if it's not actual spin, then what is it? But they could never answer that question.
When I
wanna-
was doing physics, they were talking about, in quantum mechanics, they were talking about it as an abstract quantity. You know, so they don't. So it's embedded in quantum mechanics, and quantum mechanics is difficult to understand because it's
Right.
mainly following the mathematics. Like Richard Fadum said, if you say you understand quantum mechanics, you don't understand quantum mechanics. They can follow the mathematics. They've done some. Like the Copenhagen interpretation was say, it was basically a complicated philosophy, which says don't calculate and don't ask questions, because they quantum mechanics made a mockery of language. Up is down, left is right, a circle is a square. It just, and David Bohm and his group were trying to. He was thinking of inventing a new language so that we can understand quantum mechanics, what he called Rio mode. And he noted he visited the Blackfoot tribe in Canada in the 90s. I think it was the 1990s, or I think it was the early 1990s. I can't remember when. And he thought they were speaking. He tried to invent a new language called Rio mode, and he thought that the Blackfoot tribe and the Native Americans were speaking a language very close to Rio mode, like a verb-based language.
That's interesting.
The Blackfoot. He called it Blackfoot physics by David.
So Amber, I can answer that question for you. When Brendan does the two-dimensional Turing wave simulation, there's in the middle, there's a blue line, and you have to create a gradient. So we're back to talking about gradients. And when you create a gradient, there's the opportunity for spin to happen. And yes, everything does spin. Absolutely.
So in quantum mechanics and physics, when they're teaching physics, they show you it as something spinning, just as in a simplistic way. But when you come down to mechanics, it's more abstract than that. It's difficult to understand. So Paul is saying it's actually much simpler. Paul is saying it is actually spin. It's the vortex of the ether. So we're not dealing. The quantum mechanics has up spin and down spin, and it's what was I going to say? It represents. It's supposed to represent the magnetic properties of materials. And what else? I was going to say something else about it. Spin is intrinsic angular momentum.
So
it means inside is inner angular momentum. So that's what they.
I can give you an insight into what I'm talking about here, because someone in the other group that we're in is working on graviton research for the US government or US Air Force. He's a defense contractor. And we've had conversations about it. Essentially, it's all about spin. And when the spin reaches the speed of light, this is when a graviton is formed. And gravitons are very, very powerful for propulsion, but it doesn't necessarily have to be used that way, because the way that Stavati is doing it essentially is, if you really want to understand how it works, you're using magnetohydrodynamics to make this happen essentially. So it's actually not a true anti-gravity setup, even though I call it anti-gravity. It's actually not. You get true anti-gravity when you counter-rotate things, as in the Nazi flying bell. And of course, my mentor, Bill Mueller, he was in the Hitler Youth and he saw the Nazi flying bell. He understood how it flew. He understood all the physics of it. And in the 1980s, he mentored me with all of this. So I have a really good understanding of how it works. But they're using charge clusters essentially to charge clusters are used like a clutch. Like when you engage the clutch of a vehicle, that's when you apply the power. Well, charge cluster is actually the clutch that engages the ether that allows us to do work. So that's why I talk about charge clusters a lot. And I do want to have a presentation where I talk about etherons, charge clusters, and ball lightning, how they're all one and the same. They're just fractals of each other. And when I presented that with Chris Beskar, he agreed with me. So a lot more research needs to be done and looked at that very specific thing. But it is.
I was going to say, go on, Eddie, you go
on. Yeah, it is definitely about spin. It is that gradient that we're looking for that causes a vortical motion, because it is about vortical spin essentially.
I mean, the one thing that Paul's doing is he's showing that the continuity of fields, you know, the fact that you could, in particle physics and conventional physics, you have point particles. The particles are treated as points, as mass points, and that charge is just a name. They just have they don't know what charge is. They're just given it a name.
That's the problem.
And also, Paul, with the ether, you can see how the particle is just an oscillation in the ether.
Yep.
So you can explain
exactly.
how the photons are the protons are propagating through the ether. In conventional physics, they have a vacuum, and they don't quite understand how the photon can propagate through a vacuum. It's just some kind of trick of quantum mechanics that they don't understand. The quantum mechanics can explain a certain amount, and it does get it right to a certain extent, but it's incomplete. It's just a trick of quantum mechanics that they don't understand. So Paul's going deeper, subquantum mechanics. Actually, this is what's really going on, and it's showing it's showing more things. Quantum mechanics is just limited. It can do quite clever things. I'm not taking that away from it, but it's limited in what it can do.
I always said that when I talk about subquantum kinetics to people that don't know what it is, I always say that Paul was an astrophysicist and a quantum physicist who asked the question, what makes up the quantum? And so that's where he's gone below the quantum level, and this is where subquantum kinetics comes from. And subquantum being below the quantum level, but kinetics means motion. So here we've got this motion, and Brendan is absolutely right. They don't know what charge or virtual charge is. And this is a really big part of the problem. So next time we'll do another 10 pages, and that will be part 3. And are there any more questions before we stop the recording we can talk about? Or
I was just going to read out that thing that let's just see if I got it. I was just going to read out.
Okay. See that middle line. Sorry, could you go back to that?
Go on.
Could you go back to that? The simulation of the Turing wave.
That's just pause. I don't know how to. Let's just go. Let's go see if it's there.
Okay.
That one there. That one there.
Yeah. Because if you look
here,
right there in the middle, that is the gradient. So you've got the thing on the top, the thing on the bottom, but that hump through the middle, which is a well, that is the gradient right there. And Brendan would have to, in the 3-dimensional, for example, would have to pick all the proper parameters to make the particle stable, but also have that spin, that gradient. It has to be there, otherwise there's no asymmetry, essentially. Asymmetry is what's important.
Eddie, I was just going to quickly read out this. So this is Paul's. This is where we've Paul's paper down. This is the main part of the site. So just quickly read out this from this document, this report I made of Paul with Paul. Paul and me put this together. I had the idea, and then Paul sort of tidied it up.
Excellent. Excellent.
So this
Thank you.
is what Einstein had written. This surprised even Justin. He hadn't heard of that before. He didn't recognize it. So let me just go down to what Einstein wrote about,
Yep.
which is the key to sort of subquantum kinetics and the convention, and it's different from it. So Einstein wrote, for example, this fragmentation of physical theory was noted by Einstein, who wrote, in Newtonian physics, the elementary theoretical concept on which the theoretical description of material bodies is based is the material point or particle. Thus, matter is considered a priori discontinuous. When in the second half of the 19th century, the laws of electrodynamics became known, it turned out that these laws could not be satisfactorily incorporated into the Newtonian system. The introduction of the field as an elementary concept gave rise to an inconsistency of the theory of electrodynamics as a whole. Maxwell's theory, although adequately describing the behavior of electrically charged particles in their interaction with one another, does not explain the behavior, does not explain the behavior of electrical densities, i.e., it does not provide a theory of particles themselves. They must therefore be treated as mass points on the basis of the old theory, Newtonian physics. Combination of the idea of a continuous field with that of material points, discontinuous in space, appears inconsistent. So he said Einstein believed that Paul was writing it. Whoopsie. Let's get this. So Paul was writing, Einstein believed that physical reality of space would be best represented by a continuous field, and that all physical phenomena, including particles, could be described by the appropriate solutions to the equations representing this field. Okay, i.e., what Paul's trying to do. So we go down here at the bottom when he talks about spin, because that's what Paul felt was most important for Starburst.
Yep.
Sort out spin. Here, Paul, this is Paul's, I wrote some of this, but Paul wrote half of it. Okay. Over the past year, our group, the Model G Vortical Motion Group, has been attempting to progress subquantum kinetics by including vortical motion or rotation into the reaction diffusion equations in the hope of modeling quantum particle spin. SQK theorized that the ether vortex would develop in the particle's core, and that this produces what physicists refer to as particle spin magnetic moment. Achieving this would make Model G, i.e. SQK, more physically realistic, thus upgrading it and allowing it to describe science and technologies at the quantum level. At present, physics has no official conceptual model of what spin is. It just assumes it as a property of subatomic particles. SQK goes further to explain the details of how spin forms. Currently, we're also working to simulate Model G in 2 or 3 dimensions. We hope that this will eventually allow us to simulate solitons that demonstrate the ability to elastically scatter from other solitons in a way similar to what takes place in the physical world at the subquantum level. Okay. That's that. So,
awesome. That's awesome. Thank you for that. It's so awesome to hear both your and Paul's words got to do with, because it is all about spin.
Paul wrote the important parts of that.
Yep. My understanding, and this might sound a little bit strange, Chris Beskar talks about the one electron theory and how I'm going back to etherons, charged clusters, and ball lightning are all one and the same. Chris Beskar has this one electron theory, and he's basically saying what we have to look at this differently. Perhaps we only have this one electron, and with modeling or using it in different ways, we can create all of these different properties from it, essentially. And so when I think Paul starts talking about protons with their positive charge and electrons with their negative charge, we might have to look at the fact that it might just be an electron, simply an electron, just one simple thing that gets charged, 2 different ways, essentially. And then, like I said, once you spin it up past the speed of light or at the speed of light, then it changes into a graviton. And so this is something that maybe we should have a look at in the future. This one electron theory, because this comes from Chris Beskar and Stevati Aerospace, David Wilcock. They've spent a lot of time looking at all these things. So in the future, I can talk a little bit more about that, and we'll have some different shows about it and stuff. Yeah, so that's fantastic, Brendan, that you're able to bring in Paul's actual words, because you know exactly where to find it, you know, in the books and that. Of course, because you're, you know, editing the 6th edition of Subquantum Kinetics, which will be available sometime this year to everyone for around $100, I think.
Yeah, we'll go at $89. So
$89.
It costs about $34 to print it.
Yeah, beautiful. And it is a hard cover edition with color pictures. It's going to be beautiful. And I can hardly wait for it. Hardback
Copy with color pictures.
Yep, which is fantastic. So are there any other points or anything else that anyone wants to bring up about what we talked about today?
No, I think that's all. I think it was very good. Well done, Eddie.
Okay, perfect. Well, thank you everyone for being here and listening, and maybe we can stop the recording now and then we can just chat more.
Oh, okay, I'll stop it now. Where's the stop? Pause, stop.